Hello everybody, this is me again, Yusuf Saleh, chemistry teacher. Today we're gonna study the remains or the rest of the section 1, chapter 4, and today's topic is enthalpy of formation. Okay, enthalpy of formation, we knew the enthalpy means amount of heat stored, but here we have enthalpy of formation of enthalpy change of formation, delta HF. What does it mean, enthalpy of formation? We know that chemical compounds composed of three elements that combine to form a molecule, for example, which means three elements combine to form compounds. So, amount of heat that released or absorbed, which means transferred, through this process of formation, 1 mole of a given substance called delta HF or enthalpy of formation. So when 1 mole of a compound formed, when 1 mole, it's a condition here to have 1 mole, formed from what? From combination of its three elements. But they must be, the three elements must be at their standard states, which means their physical states at room temperature at 25 Celsius. So let's repeat the definition. It is amount of energy as heat that released or absorbed when formation of 1 mole of a given substance from combination of its three elements. Okay, how to make an equation or when delta HF is given. Delta HF, which means enthalpy of formation. We start first, we put a mentioned substance, so for example, carbon dioxide, CO2. We put 1 mole in the product side, which means the coefficient of the product must be 1 and nothing else. Only 1 mole of the given substance in which side? In the product side. Okay. We put the three elements that compose this compound. So for example, CO2, we have carbon, C, and oxygen, O2. Gases must be written as diatomic. So for example, we have oxygen written as O2, fluorine as F2, chlorine as Cl2, nitrogen as N2, and so on. Gases elements must be written as diatomic molecules. Okay, when we balance the equation, we keep the coefficient of the product 1, but we can add any coefficient for products. For products, we can use any coefficient, even if the coefficient is a fraction. Fractions are allowed here. Fractions are allowed in all thermochemical equations. Why fractions are allowed? Because in thermochemistry equations, we deal with moles, not with atoms, with molecules, or with ions. No, we deal with moles. So when it is written CO2, it's okay if you have half CO2, for example. Why? Because you express a mole of CO2, or when you say hydrogen, okay, hydrogen is 1, oxygen, half mole of oxygen. It's okay to put 1/2 of O2. Why? Because you express half mole, not half molecule, and so on. So you can use the coefficients when writing the thermochemical equation of delta HF. Let's move and have some practice. We have an example here. We have here H2O, but this must be liquid actually. Let's correct this. Why? Because delta H for the liquid different from the gas. The gas is less than this. Okay, now this equation is equation of formation of 1 mole of what? H2O, from 1 mole of H2 and half mole of O2. You see that the coefficients can be fractions. Coefficients in thermochemical equation can be fractions. We don't say here we have one molecule of hydrogen with half molecule of oxygen. No, we will say here 1 mole of hydrogen and half mole of oxygen producing 1 mole of H2O, and the delta H of the reaction, which means the delta HF here is negative 286 kilojoules. So 286 kilojoules released because it's negative when formation of 1 mole of H2O from its free elements at their standard state, because they are gas and gas at room temperature. So delta H here equals delta HF. Why? Because we have formation of 1 mole of a given substance from its free elements at their standard states. Okay, now what if we have more than 1 mole? If we have more than 1 mole, the delta H of the reaction must be divided by number of moles. So for example, if you have 100 grams of water and you know the delta H, okay, how can you calculate the delta HF? Convert it into moles, divide the mass by molar mass, 100 divided by 18. Later you will say the delta HF of one molecule, of course, means the whole delta H of the reaction divided by number of moles. Let's move forward and see what we have more. We have here, when mole is 1, delta HF equals delta H by 1, so that in this case delta HF equals delta H. In this case we have 1 mole. So for example, the delta H of formation of 18 grams of water, it's delta HF. Why? Because 18 grams of water equals 1 mole of water. So in which case delta H equals delta HF? When the product involves 1 mole only, no less, no more of the product. Okay. Now, delta HF of CO2, okay, we have here this example. In this example, two carbon moles, not molecules, with 2 moles of O2. You see that we wrote oxygen as diatomic. Why? Because it is gas. But the elements not gases, we can write them as single atoms. For gases, always diatomic molecules. It produces 2 moles of CO2, and the delta H for this reaction is negative 786. Negative 786. So how can we find delta HF, which means type of formation of CO2, of 1 mole of CO2, of course. This is formation, the enthalpy of formation of 2 moles. So delta HF here, delta HF of CO2 equals delta H of the reaction, delta HR, divided by what? Divided by number of moles. How many moles of CO2 produce? 2. So we're gonna divide what? We're gonna divide the negative 786 kilojoules by 2. So this equals negative 393 kilojoule. Now we can say per mole. Why? Because this amount of heat is released on formation of 1 mole of CO2 from its free elements, from carbon and oxygen. Okay, let's move forward and see more. Let's have another example here. Another example of well formation of any substance. For example, if it's required to write delta H of acetylene. Okay, delta H of acetylene, if we want to write the equation of delta HF of acetylene C2H2, and it is given to be it is given to be positive 200 about 26, but it's positive kilojoule per mole. How can you convert this data into a thermochemical equation? First, you have acetylene, also called ethyl, 1 mole. So put in the product side after the arrow C2H2. Okay. What are the three elements? We have carbon, which is solid at room temperature, plus hydrogen, H2, diatomic. Why? Because it's gas. This is gas. And get it balanced. We have 2 carbons, so put 2 here. But hydrogen is already balanced. Okay. Here we can say the delta HF is positive 2 to 6. Or we can put the 226 in reactant side. Why? Because it is endothermic. It is one of the compounds that has positive delta HF. Most of compounds have a value of delta HF negative, but some of them have positive delta HF values. Now let's talk about the relationship between the positive and the negative value with the stability of compounds. Of course, most of compounds are stable. That's why they have negative delta HF values. Let's move forward and have a look at it. So we have stability and enthalpy of formation. Okay. Now, compounds with delta HF large negative, such as CO2. CO2 has negative 393.5 kilojoule per mole. They are stable. So when delta HF is negative or highly negative, it's more stable. Less negative, less stable. Compounds with delta HF small negative, or positive value, that are not stable. Okay, for example, we have Hi, hydrogen iodide. Easily decomposes to what? To iodine and hydrogen due to the high value of delta HF. Actually, high value means here the positive value. Its value of delta HF, value of formation, is positive 26.5. That's why it is not stable. Okay, let's compare CO2 with CO, carbon dioxide, with carbon monoxide. We have delta HF, of CO2 equals negative 393.5 kilojoule per mole. But delta HF of carbon monoxide, CO, equals negative about 110 also kilojoule per mole. So which one is more stable, which one is less stable? Of course, carbon monoxide, dioxide is more stable than carbon monoxide, and this is the reason why carbon monoxide is dangerous. You know, if you inhale carbon monoxide, it will take oxygen. Of course, inhale it, so it will take oxygen from your brain. Instead of formation of oxyhemoglobin and transfer oxygen to brain, it will go to the brain, of course, after forming carboxyhemoglobin, and takes oxygen from your brain. So your brain will have lack of oxygen, and if this continues, the person will get in coma and may cause death. So you see that it is unstable. That's why it is dangerous. Okay, let's have more examples about the stability and delta HF. It is written here that HF of CO2 is about negative 393 moles. Is it stable? Of course it's stable. We have acetylene. We just talked about acetylene is C2H2. It has delta high positive. Its delta HF we mentioned is positive about 226 kilojoule per mole. So is it stable or unstable? Certainly it is unstable because it has high positive. Certainly it is unstable. This gas is being used acetylene for the welders use it for cutting and welding the metals. We have another one with very high delta HF. We have mercury fulminate. Mercury fulminate at GC2N2 O2 has delta HF of positive about 270 kilojoule per mole. It is completely unstable, and this is used in igniters of explosives, or they say detonators, which means the starting of the explosion, or the starter of the explosion. Why it's unstable? Because it has a very high positive value of delta HF. Okay. I have a question here in section review. Describe the relationship between the compound stability and the enthalpy of formation. Of course, here is inversely proportionality, because the high value of delta HF, of course, the high is the positive, so it's unstable. And the high negative, which means the low, very low value of delta HF makes the compound stable, such as CO2, carbon dioxide. Let's have a look on the answer here. Okay. Sorry. The answer here, as the compound's enthalpy of formation has a greater negative value when it is supposed to be more stable, greater negative value. And when it has a greater positive value, it will be unstable. So the enthalpy of formation, delta HF, is inversely proportional with stability. Okay, this is all about the enthalpy of formation, but it's very important to know how to convert the delta HF of any compound to a thermochemical equation. Why? Because you're going to need it in coming topics. Now let's move to next topic, which is enthalpy of composition. We know that composition means burning something, or totally burning, or complete burning of something. So enthalpy of composition is delta Hc. For enthalpy of formation, we use delta HF. This is delta Hc. What is delta Hc? It is amount of heat that released when burning 1 mole of a given substance in sufficient oxygen, enough oxygen. Of course, it will form oxides of the elements in this compound. So there's a condition here to have only 1 mole of the burned compound, of course mentioned in the question, to have only 1 mole in the reactant side with enough oxygen. You can use any coefficient to balance oxygen, including the fractions. And the product side, you're going to have the oxides of the elements in this compound. Let me repeat. When you write the thermochemical equation of a compound, thermochemical equation of delta Hc, enthalpy of composition of a compound, we put in reactant side what we put, 1 mole of the burned substance, of the burned compound, for example, and enough oxygen. To write, we're going to put oxides of the elements. If we have an organic compound and burned, we have delta HF of it, always the products are CO2 and H2O because it is carbon oxide, carbon dioxide, and H2O is oxide of hydrogen. So any compound containing hydrogen and carbon, or hydrogen and carbon and oxygen, always the product are CO2 and H2O. Okay, so let's move forward and see how to apply this information. Of course, here the composted, which means the burned substance must be in the reactant site and only 1 mole. With what? With oxygen. With sufficient oxygen. So for example, if you have delta, we said delta Hc of carbon is negative 393 kilojoule. How can you convert this into a thermochemical equation? We put 1 mole of carbon with enough oxygen. And the product, of course, it's oxide of carbon because it is combination with oxygen. Okay, when we balance, it is already balanced. We have 1 mole and 1 mole of oxygen. Now, this is delta Hc of carbon. It is also formation of 1 mole of CO2. Formation of 1 mole of CO2 from its 3 elements. Here, delta HF equals delta Hc. Delta HF equals delta Hc. Why? Because the equation represents the burning 1 mole of carbon and also formation of 1 mole of CO2. So in some cases, the delta HF equals delta Hc. Okay, now also of formation of 1 mole, just we said 1 mole of CO2 combines by releasing the same amount that released, same amount of energy as heat that released when burning 1 mole of carbon. Let's have an example here. We have delta Hc, of course, we have delta Hc equals delta H divided by the moles reacted or the moles burned, which means when you have amount of substance that burned and you know the delta H of the reaction and you want to find the delta Hc, just divide the delta H of the reaction by the moles that burned, that reacted. Okay, let's see more practice. Okay, this example, sorry. And the reaction below, we have 3 carbon moles burned with enough oxygen producing 3 CO2 molecules, and delta H is negative 1179. So can you calculate the delta Hc of carbon or delta HF of CO2 from this equation? Definitely yes, because when you divide the equation, you're going to have the equation, thermochemical equation of burning 1 mole of carbon. So just divide this by 3. Divide it by 3. Why by 3? Because you used 3 moles of carbon and also you produced 3 moles of CO2. So the solution here, delta Hc equals delta H, which is given, divided by the moles reacted. We have 3 moles of carbon is burned and also 3 moles of CO2 produced. Okay, let's move forward and see more examples. Okay, here we have, looks like there is a mistake here. The one given here, sorry, it represents delta HF of CO2. So what is the delta HF here? Equals the delta H of the whole divided by number of moles. So here the delta H of the reaction, delta H of the reaction equals delta HF times the moles, and delta HF is given. And how many moles burned? 2. So just multiple by 2 equals negative 786. This amount of heat is released when burning 2 moles of carbon. Here we have 2 moles of carbon. Okay, now enthalpy of reaction. this is all about the how to convert the delta H F into thermochemical equation and delta HC into thermochemical equation. And I will repeat, we will need them. We will need how to convert them when we calculate the enthalpies of reactions. So let's move forward and see how to convert, how to find or how to calculate the reactions enthalpy. Actually, enthalpy of reaction, or delta HR, equals amount of heat transferred, which means may be released, may be absorbed during a chemical reaction. How can we calculate it? We have two possibilities. We have two ways, depending on the given data in the question. So the first procedure, if the question involved enthalpies of formation of reactants and products, In this case, we will say delta H of the reaction equals sum of delta HF of products minus sum of delta HFs of reactants. You might see it in some books written in, sometimes they say sigma delta HF of products. Of course, these products, each one multiplied by its coefficient minus sigma, which means the sum of delta HF of part of reactants. The question will not give you something. What is the data will not be given? Free elements, such as these here, aluminum, mercury, iron, oxygen, hydrogen, these have delta HF values of 0. So don't seek them in the question, because they will not be given. Why? Because simply you must know that they are 0. They have delta HF values of 0. The rest will be given. If given, you can use this procedure. So each substance in the products, multiply it by its coefficient in the chemical equation, minus each substance in the reactant multiplied by its coefficient. Let's have a look at some rules here, or some notes here. We have here, we talked that delta HF of free elements are 0 kilojoule. Other elements are written as monatomic ions. We have some elements other than gaseous elements are written as monatomic ions, but we have phosphorus will be written as P4, and sulfur will be written as sometimes as S only. If you see it as S, it's for simplifying, for simplicity. Anyhow, now let's see this practice problem. Okay. In this practice, it says calculate delta HC of methane gas. Delta HF values are given. Of course, this is methane is CH4 given here. And delta HF values are given respectively for methane CH4, water H2O, CO2 are going to be negative 75 is the delta HF for CH4, and negative 286 for liquid water, and negative 393 is for CO2, or are kilojoule and more. Of course, this is respectively, which means the first is the first, the second is for the second. The solution, we're going to apply the rule, the mathematical relationship we just mentioned. The delta H of the reaction equals sum of products, delta HF of products minus our reactions. But here we have a free element here. This free element has 0 kilojoule. So just ignore it. Ignore this. You will say delta HF of CO2 in a big bracket plus delta HF of H2O times 2 minus delta HF of CH4 also times 1. So you can see here for products 2 moles of H2O, okay, delta HF of H2O times 2. Delta HF of CO2 times how many? Times 1. Delta HF of CH4 present. For H2, for O2, it is written here, but if you ignore it, it's okay, right? Because it's already 0. It's going to be 0 here. So the sum will be the delta H of this reaction. So let's move forward and see the, oh, sorry. Okay. Okay, we can see that delta Hc of burning of CH4 is negative because it is actually organic and it has all of them, all organic compounds have delta Hc of negative because they release energy as heat. Besides, CH4 methane is a part of natural gas that we use for cooking and lighters. So it's normal to have negative and high negative value. Okay, let's have more examples here. We have an example says calculate enthalpy of composition of nitrogen monoxide. Okay, nitrogen monoxide is NO. Okay, NO that results producing NO2 and the thermochemical equation below. We have NO with half mole of O2 producing 1 mole of NO2. And given the delta HF values, delta HF of NO2 given to be positive 90.3. Why this is positive and why this is positive? Delta HF of NO2 is positive. Delta HF of NO positive. Delta HC of nitrogen is also positive. You know, nitrogen is one of the elements that has rare delta HC value. It is hard to burn it. It is hard to combine it with oxygen. And that's why the highest percentage of air components is for nitrogen. You know that nitrogen has percentage of 78% of the atmosphere. Why? Because it is stable. It doesn't tend to react with other elements. It doesn't tend to oxidize. Why? Because it has positive value of composition. Okay, now let's move forward and apply the rule. We have the products minus the reactants, the products, 1 2 times how many? Times 1. Okay, minus the reactants of times 1. And here we have oxygen is 0. So you can ignore it because already is 0. Let's see the result here. The delta HF of the product is less than the delta HF of the reactants, so it's supposed to be negative. Okay, it is negative 5. I think this is enough for this mini lecture. By next mini lecture, we're going to study the second procedure to find the enthalpy of reaction and called Hess's law. It requires more work than this procedure. So I wish to meet you again on next mini lecture and have a nice day.